In this video, we are going to solve a polynomial inequality. And I'm going to demonstrate both methods of solving this inequality. The first is graphically, and the second method is algebraically using the interval test method. But if you already know that you prefer to solve polynomial inequalities algebraically, then please go ahead and fast forward the video so you can see the second method. So whenever we're starting with a polynomial inequality, we first want to write it as an expression compared to 0. So in this case, that means I would need to subtract 4 from both sides, which would give me x cubed plus x squared minus 4x minus 4 is greater than or equal to 0. So now we're going to look at the left-hand side, this expression, and we're going to treat this as a polynomial function. So we're thinking about visualizing what the graph of y equals x cubed plus x squared minus 4x minus 4 looks like. And then once we have the graph, we're taking a look at the part of the graph that is greater than or equal to 0. And on the graph, that's going to be the portion, or portions, if there's more than one, of the graph that is above the x-axis. So we're taking a graphical approach using our knowledge of what the graphs look like for polynomial functions, and then using the graph to help us basically solve this inequality. So we want to begin by finding the zeros. So setting this function equal to 0. When we set y equal to 0, that really means we're finding the x-intercepts. So setting y equal to 0, we have an equation to solve. And this is a cubic equation, and it has 4 terms on the right-hand side. So we'll begin by trying to factor. We'll always start with factoring as our first method and see if it works. So since there's 4 terms, we're going to factor by grouping. So if we group the first 2 terms together, we can factor out an x squared and be left with x squared times the quantity x plus 1. And if we group the second 2, or I should say the last 2 terms together, we can factor out a negative 4, and we will be left with negative 4 times the quantity x plus 1. Now we're going to factor one more time. This time I'm looking at the first term being x squared times x plus 1 and the second term being negative 4 times x plus 1. And I notice that they have a common factor of an x plus 1. So I'm going to factor out an x plus 1, and then I'll be left with an x squared minus 4. So that was factoring by grouping. Then I noticed that x squared minus 4 is a difference of perfect squares. So I can actually factor that factor a little bit further. X squared minus 4 will factor into x plus 2 times the quantity x minus 2. So from this factored form, I can see that I have 3 zeros, 3 x-intercepts, which would be negative 1, negative 2, and positive 2. And each of these x-intercepts appear just one time. So we don't have any multiplicities here. So now I'm going to go ahead and begin constructing my graph. So I will plot my x-intercepts, negative 2, negative 1, and positive 2 to start with. Now let me go back up to our function. So when I say I'm looking at the function, I'm looking at y equals the x cubed plus x squared minus 4x minus 4. And I want to think about the shape of a cubic function. So we know a cubic is an S-shaped curve, and because we have a positive 1 as my leading coefficient, try that again, positive 1, there we go, as my leading coefficient, then that tells me about the end behavior of this graph. It's going to be an S-shaped curve that eventually rises. So when you look at the far right-hand side of this curve, the right-hand side is rising. It rises to the right, it falls to the left when we look at that end behavior. So using the end behavior and the x-intercepts, I can create a nice rough sketch. This is a cubic curve, kind of an S-shaped curve. It's again a rough sketch because we're just using the graph to help us solve the inequality. Now, we were interested in, going back above, the portion of the graph that was greater than or equal to 0, which means we're looking where the y values are greater than or equal to 0, and that corresponds to the portion of the graph that is above the x-axis. So if you get out a highlighter, highlight the portions of the graph that lie above the x-axis, and you'll see there are two portions of the graph that lie above the x-axis. So my answers for the inequality are the x values that lie in these two regions on this graph. So looking again at those x-intercepts, which were -2, -1, and then +2, I am looking for all of the x values between -2 and -1, and then all of the x values bigger than 2. So my answer is going to be an interval or intervals. In this case, we're looking at x values from -2 to -1, and then all the x values from 2 to infinity. Now, I have purposely left out my bracket or parentheses because I have to think about that. That's another layer. I need to think about whether I should include. Do I want to include these x-intercepts or not? And that all depends on the inequality again. Because this is greater than or equal to 0, we want to not just be above the x-axis, but also on the x-axis where the y value is equal to 0. So that implies that we are going to include. We will include those x-intercepts, and that's why we choose brackets. So a bracket, -2, -1, union, bracket 2 to infinity will be our final answer. So that's how to solve a polynomial inequality graphically. So next, let's move on to the second method, which is how to solve a polynomial inequality algebraically. And some teachers and authors call this the interval test method. But this method actually begins very similarly to solving graphically, in that we still have to begin by writing the expression compared to 0. So I still have to subtract 4 from both sides to have x cubed plus x squared minus 4x minus 4 is greater than or equal to 0. And then I still need to find the values where f of x is equal to 0. So I essentially am going to go ahead and change this inequality temporarily. I'm changing this to an equal sign, so I'm solving to find where this is equal to 0. We're basically finding the zeros. We will still solve this by factoring by grouping. So factoring out an x squared, and we'll have x squared times the quantity x plus 1. Then we'll factor out that -4 and be left with -4 times the quantity x plus 1, and then factor one more time. And at this point, you're probably realizing that the algebra looks the same so far, and it absolutely is. If I continue to factor the difference of perfect squares, so I factor x squared minus 4 into x plus 2 times x minus 2, and I still get these zeros to be -1, -2, and 2. So far, the work really does not look any different. The difference is our next step, because now, rather than actually graphing the entire curve and thinking about the shape, we're just going to be looking at essentially a number line, and you can think of this number line like the x-axis, and I'm going to place these values on the number line, and I'm putting them on the number line from small to big, so in increasing order. And let me mention, I was calling these values the zeros, and there are some people that also refer to them as boundary points, if you've heard those expressions. They can be also called boundary points. And basically, we are just going to test around these boundary points, around these zeros, and we're doing a sign analysis so we can figure out which intervals give us positive outputs and which intervals give us negative outputs. Because ultimately, we're interested in outputs that are greater than or equal to 0. So we want positive outputs. And we're going to do a sign analysis to figure out which intervals give us those positive outputs. So we are basically going to choose some test numbers. So I need to test numbers that are in this interval here, and those will be values that are less than -2. So I can pick any value that is smaller than -2. So I'll go ahead and choose -3. Next, I need to pick a test value that is between -2 and -1. So a value like -1.5 would be fine. Next, I need a value between -1 and 2 in this interval. So 0 would be a nice value there. And lastly, I need a value in this final interval that would be greater than 2, so I will choose +3. So now, when I actually go to do the testing, I'm going to take these test values and I'm going to substitute them back into the factored form that I had up here, which was x plus 1 times x plus 2 times x minus 2. So I'll begin with -3, and I'm substituting -3 in for x. So if I substitute -3 plus 1, that will get me -2. Now I'm not actually going to write down the value, but rather I'm just going to keep track of whether or not the value is positive or negative. So that first factor, x plus 1, when we substitute in -3, we get a negative output. When I substitute -3 in for x here, -3 plus 2 is also another negative output. So right now I have a negative times a negative. When I substitute -3 in for x minus 2 in for x, -3 minus 2 is a negative. So I end up with a negative times a negative, which will be a positive, times another negative, which results in a negative output overall. So what that means is any value that I choose that's smaller than -2, any value smaller than -2 will produce a negative output. So I'm going to put a little minus sign, and I like to put it actually below the number line because I automatically sort of think graphically myself. I just can't help it, to show that if I'm getting a negative y value, I know that part of the graph is going to be below the x-axis. But I'm just going to put a minus sign. You could put it technically above the number line if you wanted to, and that little minus, that negative, tells me that the outputs will be negative. Now let's move on to my next testing value, which is -1.5, and we'll do the exact same thing. So we substitute -1.5 in for x. -1.5 plus 1 will be a negative output. -1.5 plus 2 will be a positive output. -1.5 minus 2 will be a negative output. So this time we have a negative times a positive times another negative, which ultimately will leave us with a positive output. So that means any number chosen between -2 and -1 yields a positive output. So I'll put a plus sign in between -2 and -1, and again, I like that plus sign to be above this number line. Let's keep going. Now we're going to test 0. So testing 0 again in for these x values. 0 plus 1 is positive. 0 plus 2 is positive. And 0 minus 2 is negative. So overall, that results in a negative output. So I'll put a minus sign. And final testing number is 3. And if we substitute in 3, 3 plus 1 is positive. 3 plus 2 is positive. 3 minus 2 is also positive, so overall we get a positive output. So we call this a sign analysis. It's also called the interval test method. And once you've done your sign analysis and you have tested around your zeros, around your boundary points, then you can go back to the inequality, not the original inequality, but the one that was compared to 0. So the one here in my first step where I said it was greater than or equal to 0, which means I'm looking for positive outputs, and we can highlight the intervals that give positive outputs, which would be between -2 and -1 and greater than 2. And then once again, because of the equal to here, it's not just greater than, it's greater than or equal to, then we want to include the zeros, which means we will use brackets on all of those zeros. And then that sign analysis is complete and we can write our final answer. So all of the x values that are elements of the interval from -2 to -1, unioned with 2 to infinity, will produce positive outputs. So these will be the solutions to the inequality. And side by side, let me just show you one more time the comparison so you can really see clearly how these are related. Hopefully you can see, looking at the graph and our sign analysis, when we had the minus sign, try again. When we had this minus sign, there it is, that negative meant that we had negative outputs, and that really corresponded to the portion of the graph here that was below the x-axis. And then we had a positive, which corresponds to the portion of the graph above the x-axis. And then we ended up with a negative again, that corresponds to the portion of the graph below the x-axis. And finally, that last positive, which corresponds to the portion of the graph above the x-axis. So you can see how these methods relate to one another. Graphically is clearly a visual approach, and then doing it with the interval test method is more of an algebraic approach. But both work beautifully. You just need to figure out which one works best for you.